Hello, this is the fifth video on my honors linear algebra and multivariable calculus. In this video, we're going to go over the idea of subspaces, linear independence, generating, and bases, and we will do some examples. So here's a reminder from the last video. We talked about Rn as a vector space, and we said it satisfies these 7 properties. It satisfies closure, associativity, commutativity. It has an additive identity. Every element has an additive inverse. It satisfies distributivity, and it has the multiplicative identity of 1. So the idea is that if you take a subset of Rn that it satisfies all of the same 7 properties, then it would be called a subspace. So first, what is the definition? And then we will do a theorem, and then we'll talk about a couple of examples. A subset W of Rn is called a subspace of Rn if W along with the same operations of Rn satisfies all properties of a vector space. In other words, the 7 properties that we listed above. In other words, if you take every 2 vectors in that subspace, the sum and the scalar multiple would be in the same subspace. So what we gotta have to do is to replace this with our subspace, let's say V. Everywhere I have Rn, I will have to replace it with V. If I take 3 vectors in V, then it satisfies the associativity, which is basically obvious because it inherits the same property from Rn. Associativity can be inherited. Again, here we replace this one by V, here we replace this one by V, and if it satisfies these properties, then it would be a subspace. And just to make sure, this 0 vector would have to be in the subspace V. Otherwise, there would not be the additive identity inside the subspace. Okay, so the main criterion that we can use in order to show something is a subspace is what we call the subspace criterion, because the alternative would be to just check that it satisfies all of those 7 properties, and of course that's quite cumbersome, so you'll have to go through every single one of them one by one and check them. But there's actually a much faster way of showing that something is a subspace. So what is the subspace criterion, and how do we prove that? A subset W of Rn is a subspace if and only if it satisfies all of the following conditions. So basically there are 3 conditions that must be satisfied. The first one is that W must contain the 0 vector, and the second one is that W must be closed under addition, and the third one is that it must be closed under scalar multiplication. So let's go over the properties and check that it satisfies these properties. So properties of subspace are, the first one is closure. So closure is part of the assumption. So this is assumed. So we are done. The second property that we need to check is, if we look at the list, the second one is associativity. Associativity follows from associativity of Rn, because if we take 3 vectors in V, then x plus y plus z is the same as x plus y plus z. That is just given because it's true in Rn. And associativity of a times bx is the same as ab times x. That also follows from associativity of Rn. So associativity follows from that of Rn. So that's the second property. The third property is commutativity. Commutativity means x plus y is equal to y plus x, but that's exactly the same property of Rn. So that also follows from the same property of Rn. So these 2 properties are in fact inherited. So let's look at property number 5. If we look at the properties, the 5th one is additive identity. So additive identity means 0 is in V, and this is an assumption. So 0 is in the set by assumption. What did I call this set? I think I called it W. So let's put it this way. 0 is in W by assumption. That was one of the assumptions that we had. So additive identity is in W because of the assumption. The fifth one is additive inverse. So let's take some W in W. I will have to show that minus W is also in W. And the things that we know are W is closed under addition and scalar multiplication. Well, we can create negative W by multiplying W by -1. So -1 times W is in W because W is closed under scalar multiplication. And that tells us that minus W is in W. So additive inverse is also in there. The sixth one is distributivity. Distributivity also follows from distributivity of Rn, because if the set is V, and we know that, or in this case it was actually W, we know that we have the distributivity in Rn. We would obviously have the same distributivity in V because X and Y are elements of Rn. So this one also follows from that of Rn. So this follows from that of Rn. And finally, the last thing is additive identity. 1 times X equals X. This is again also follows from the same property in Rn. So really the only thing I need to show is those only things I need to show are those three things. It is closed under addition, closed under scalar multiplication, and it contains the zero vector. So keep that in mind, because anytime you want to check something is a subspace, subspace criterion is the best approach. You don't want to go over all those 7 different properties. That's very time consuming. So let's go over this example. The set of all points xy on a given line, so M is fixed, is a subspace of Rn. So we will have to show 0 is in there. Well, 0 is equal to M times 0. So that means 0, 0 is on the line. Then I need to show if two things are on the line, the sum is on the line, and the scalar multiple is on the line. Let x1, y1 and x2, y2 be on the line y equals mx, and c be some scalar. So since these are on the line, we know that y1 would be m times x1 and y2 would be m times x2, because they satisfy the equation of the line. So that tells us if I add them, I get y1 plus y2 is m times x1 plus x2, and I can multiply it by a c. cy1 would be m times cx1. So that tells us that the sum and the scalar multiple x1 plus x2 comma y1 plus y2 and cx1 comma cy1 are on the line y equals mx. So this shows that it is closed under addition and scalar multiplication. So by the subspace criterion, the given line is a subspace. And of course, this is a subspace of R2 because it was in R2. So that's the first part of this problem. The second part is asking us to show that the set 0 and Rn are both subspaces of Rn. So again, we need to show the same thing. So obviously 0 is in 0. And if I take two things, if x and y are in this set, then, well, there's only one element in there. So x and y are both 0. So that means x plus y is also 0, which is in the same set. And c times x is C times the 0 vector, which is 0, which is also in the same set. So that means it satisfies the subspace criterion. So thus, by the subspace criterion, this set, the singleton 0, is a subspace. Next is Rn is a subspace of Rn, but that's also very obvious. So Rn is a subspace of Rn with a similar method. So it's pretty straightforward. What we do is we show that 0 is in Rn. Of course, 0 is in Rn. And if you take two vectors in Rn, the sum is in Rn, and the scalar multiple is also in Rn. So that's pretty straightforward. So we have now three examples of subspaces. In general, you want to think about subspaces as lines or planes that go through the origin. So in 3D, if you look at a line through the origin, you'll get a subspace. Or if you look at a plane through the origin, you will get a subspace. So any line or plane going through the origin would be a subspace. Okay, so let's look at one more example. If W and U are subspaces of Rn, then so is their intersection. So we want to prove this one. So again, we will use the subspace criterion. So we will use the subspace criterion. We will have to show two things, or three things rather. First of all, 0 is in the intersection, and second, intersection is closed under addition, and intersection is closed under scalar multiplication. So let x and y be in the intersection and C be in R. So I'm going to show that it is closed under addition. So by definition of intersection, oh, and by the way, I forgot something when I was doing the subspace criterion. The subspace criterion is if and only if, but one direction is quite obvious. So what I showed here is the backwards direction, meaning that if something satisfies these two properties, then it is a subspace. The forward direction is obvious, because if something is a subspace, it would of course contain the 0 vector, and it would of course be closed. So that part was actually obvious. So let's look at this example. X and y are in the intersection. By definition of intersection, x and y are both in W, and x and y are both in U. But we know that U and W are subspaces. So since W and U are subspaces, x plus y and cx are both in W, and x plus y and cx are both in U, because we know that subspaces are closed under addition and scalar multiplication. But again, by definition of intersection, these vectors are in the intersection. So x plus y and cx are in the intersection of W and U. It means W intersection U is closed under addition and scalar multiplication. Now we will have to show that 0 is in the intersection. So we know that W and U are subspaces of Rn. So 0 is in W and 0 is in U. So now by definition of intersection, zero is in the intersection. So 0 is in W, intersection with U. So now we showed that 0 is in the intersection, and the intersection is closed under addition and scalar multiplication. So by the subspace criterion, we are done. W intersection U is a subspace. Okay, so this completes the proof of this problem. So we are done with the definition of a subspace and the subspace criterion. Now we want to understand linear dependence, spanning, and basis. So first, what is a linear combination of two vectors? Here's the visualization of what it is. If you take a bunch of vectors, a vector W is called a linear combination of vectors v1 through vm, if W is c1 v1 all the way to cm vm, c1 through cm are real numbers. If the set is empty, if there are no vectors in a set, we say linear combination of those vectors, which would be the empty set, would be just the zero vector. Okay, so here's an illustration of what linear combination is. So if you take a vector u, you rescale u, you rescale v, and then you add them using, for example, the parallelogram law. So this would be the c1u plus c2v. Okay, so here's one observation that helps us understand the next definitions. The next definition, and then we'll talk about a couple more definitions. We note that every vector w that is of the form x, y, z can be written as x times 1, 0, 0, y times 0, 1, 0, and z times 0, 0, 1, because the first one is x, 0, 0, the second one is 0, y, 0, and the last one is 0, 0, z. So in some ways, these three coordinates are completely independent. X, y, and z are completely separate from each other, which means these three vectors 1, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1 are in some ways independent of one another. So the next definition allows us to formalize this idea of independence. We say vectors v1 through vm in Rn are linearly dependent if one of the vectors can be written as a linear combination of the others. Otherwise, we say v1 through vm are linearly independent. So if one of the vectors can be written as a linear combination of the others, we say they are linearly dependent. If none of them can be written as a linear combination of the others, then we say they are linearly independent. So let's look at an example here. Check if the following vectors are linearly independent, linearly dependent, or linearly independent. So I want to see if these three vectors are linearly independent or linearly dependent. So I will see if one of them can be written as a linear combination of the others. I will have to check three things. 1, 0, 0 equals c1, 0, 1, 0 plus c2, 0, 0, 1. I want to see if this is possible. 1, 0, 0 equals, this one becomes 0, c1, 0 plus 0, 0, c2. And this is equal to 0, c1, comma, c2. But that tells us 1 equals 0 because the first components must be the same. So that is a contradiction. So that means the first vector cannot be written as a linear combination of the others. Of the other two. Okay, so as I assumed this is the case, and I got to a contradiction, which means 1, 0, 0 cannot be written as a linear combination of the others. Now I will do the exact same thing. So I'll write down one more of them, and then I'll leave the rest, the last one, to you. So 0, 1, 0 equals c1, 1, 0, 0 plus c2, 0, 0, 1. So if that's the case, then that means 0, 1, 0 is equal to c1, 0, the second component can become 0, and then c2. But that tells us 1 must be 0 by the second component, by looking at the second component, and this is a contradiction. So it means the second one also cannot be written as a linear combination of the other two. So thus 0, 1, 0 is not a linear combination of 1, 0, 0 and 0, 0, 1. So similarly, the last one is also not a linear combination of the first two. Similarly, 0, 0, 1 is not a linear combination of 1, 0, 0 and 0, 1, 0. So what does that mean? It means none of them is a linear combination of the others. Therefore, they are linearly dependent. Therefore, 1, 0, 0, 0, 1, 0, and 0, 0, 1 are linearly dependent. Okay, so that's the first part of this problem. We will do the same thing for the second part. We have 1, 2, 4, 3, 1, 2, 4, 3, 6. I want to see if any of them is a linear combination of the others. You'll have to just set up the systems and then see which one would work. Okay, so it's not very difficult to actually see that one of them is a linear combination of the others. I will just give you the answer. The last one is a sum of the first two. So you can kind of observe that 1 plus 3 is 4, 2 plus 1 is 3, 4 plus 2 is 6. And this is really all we need. We know that 4, 3, 6 is equal to 1, 1, 2, 4 plus 3, 1, 2. Thus, these vectors are in fact linearly dependent. And that completes the solution. Okay, now you might have noticed that for the first part of this problem, for the part that I wanted to show the three vectors are linearly independent, I had to go through three different things. So if you have, say, 10 vectors, then you'll have to try that 10 different times if each one of them can be written as a linear combination of the others. So that's pretty time consuming. And the question is if there is a better way of doing that rather than just going through exhausting every possibility. And the answer is in fact yes. So here's a better way of showing that m vectors are linearly independent. Okay, so the vectors v1 through vm are linearly dependent if and only if there are real numbers c1 through cm, not all 0, meaning that at least one of them is non-zero, such that c1 through c1 v1, c2 v2, all the way to cm vm add up to 0. In other words, what does that mean? Another way of saying this statement is if this guy is 0, if c1 v1 all the way to cm vm is 0 for some scalar c1 through cm, then c1 through cm must be 0. If that's true, then they would be linearly independent. So basically I negated that first statement. Linearly dependent means something like this: 2v1 plus 3v2 minus v4 equals 0, which means the third coefficient is 0. This would be linearly dependent. Opposite of that would be there is no such a linear combination that gives you 0. So we will prove that theorem. Okay, so it's an if and only if theorem. We will have to prove two different things. First, we are going to assume that they are linearly dependent, and then we're going to show that there is c1 through cm, that this is 0. Okay, so they're linearly dependent. What does that mean? It means one of them can be written as a linear combination of the others. So now, without loss of generality, I can assume that, let's say, Vm is a linear combination of the others, because just one of them is a linear combination of the others. So assume Vm is c1 v1 all the way to cm minus 1 vm minus 1 for some scalar c1 through cm minus 1. But if that's the case, I can already obtain a linear combination that is 0 by just moving vm to the other side. So I would get c1 v1 all the way to cm minus 1 vm minus 1 minus vm, that's 0. And negative 1, which is this coefficient, isn't 0. So since -1 isn't 0, we are done. We found a linear combination that is 0 with one of the coefficients non-zero. Now let's look at the converse of this. So I have a linear combination that is 0, and I want to show that they are linearly dependent. So suppose C1V1 all the way to CMVM is 0, and at least one of C1 through Cm is non-zero. So here's what we're going to do. We're going to assume that, let's say Vm, the coefficient of Vm isn't 0. Again, without loss of generality, we assume that Cm isn't 0. Now we're going to solve for Vm. So CMVM becomes minus C1 V1 minus Cm minus 1 Vm minus 1. Now we're going to divide by Cm. We get Vm equals minus C1 over Cm V1 minus Cm minus 1 over Cm times Vm minus 1. Okay. So what does that mean? It means Vm is a linear combination of the others, which means by definition V1 through Vm are linearly dependent because one of them is a linear combination of the others. Okay, so that completes the proof of this. Now there's a couple of related definitions to this which I'm going to talk about. So the first definition is, given a subspace V of Rn, we say a subset S of V is spanning if every V is a linear combination of some vectors in S. So oftentimes we need sets that generate or span everything in the subspace, which means every vector in that subspace can be written as a linear combination of those vectors in the set. We say a subset B of a vector space of a subspace V of Rn is a basis if it is both linearly independent and spanning. So here's an example. 1 0 0 0 1 0 0 0 1 form a basis for Rn, for R3. Well, we already showed that they are linearly independent. We showed in a previous example that 1 0 0 0 1 0 and 0 0 1 are linearly independent. So we already showed these are linearly independent. Now I will have to show that they are also spanning. So I will take one vector in R3 and I will have to write it down as a linear combination of these three vectors. So we can separate that into the three components. So 0, y0, and 0, 0, z. Then we can take out this scalar. So we get x times 1, 0, 0, y times 0, 1, 0, and then z times 0, 0, 1. So that means they are spanning. So thus 1, 0, 0, 0, 1, 0, and then 0, 0, 1 span R3. So they are spanning, they are linearly independent, therefore they form a basis. So therefore 1 0 0 0 1 0 0 0 1 form a basis for R3. Okay. So let's look at one more theorem, and this is the last thing we're going to talk about in this video. Okay, so what does this theorem tell us? Let V be a subspace of Rn. The vectors v1 through vn in V form a basis if and only if every vector in V can be uniquely written in that form. So what is a basis? It is a set that is generating and linearly independent. So here we want to show that really what it is that every vector can be written as a linear combination in a unique way, not multiple ways. And this is again an if and only if statement. So we'll have to show two different things. Okay, so I'm going to assume that it's a basis, and then I'm going to show that everything can be written and it can be written uniquely. So we're assuming that V1 through Vm form a basis for V. Okay, so because it's a basis, it is linearly independent and it is spanning. But the spanning means every vector can be written in that form. So let W be in V. Since V1 through Vm span V, W can be written as sum of Ci Vi for some scalar Ci. Now really the only thing that is left is to show that it is unique. In general, the way we want to show uniqueness in math is to show that there are two different ways and then to show that those two different ways are the same. So suppose W can be written as sum of Ci Vi I equals 1 to m and also sum of Di Vi for some Ci and Di inside R. Inside R. This is R. Okay, so we're gonna have to show that this representation is the exact same thing. So here's what we're gonna do. We're gonna move everything to the same side, so we get the sum I equals 1 to m Ci minus Di Vi equals 0. But we know that Vi's are linearly independent. So since V1 through Vm are linearly independent, all of the coefficients must be 0, because think about the theorem that we just proved. Linearly independent means if a linear combination is 0, then all the coefficients must be 0. So Ci minus Di must be 0 for all I from 1 to m. And that tells us that Ci must be equal to Di, which means the linear combination is unique, because we started from two linear combinations and then we showed that they have to have the same coefficients. These two coefficients, Ci and Di, must be the same. So we showed every vector can be written as a linear combination of those vectors and the representation is unique. Okay, so let's now prove the backwards. So we know that every vector in V has a unique representation in that form, and we want to show that those vectors form a basis. So suppose every vector W in V can uniquely be written as a linear combination of VI's. Now I want to show that in fact VI's are linearly independent and spanning. Okay, first of all, since everything can be written as a linear combination of V1 through Vn, they would have to be generating. So by assumption, V1 through Vn are spanning or generating. Okay, so that part is obvious. That's just given by the assumption. Now I will have to show they are linearly independent. So suppose sum of Di Vi is 0. In order to show a set of vectors are linearly independent, I will have to start from a linear combination that is 0, and then I will have to show that all the coefficients are also 0. So one thing you notice is that 0 can be written as the sum of 0 vi, because 0 times every vector is just 0. But by uniqueness, these two linear combinations must be the same thing. This linear combination, this linear combination must be the same thing. So by uniqueness, di must be 0 for I equals 1 through m. What does that mean? That means v1 through vm, and these are m, are linearly independent. So what we showed is that this set of v1 through vm, they are linearly independent and spanning. The spanning comes from the definition. Linear independent comes from the uniqueness. The assumption was every vector can be written and every vector can be written uniquely. The part that it says it can be written gives you the spanning part. The part that it tells you it can be written uniquely gives you the linear independence part. And this brings me to the end of this video. So I will see you in the next video.